Okay, so in Notes 3.2, we're going to introduce a new set of numbers called the complex numbers. Up until this moment in math, in your real lives, you thought you knew of all the numbers that ever existed. And I'm here to tell you today, no, you don't know all the numbers that exist in the world. There's this bigger, larger set called the complex numbers. Okay. Our objective is we want to be able to simplify complex numbers. We want to be able to add, subtract, and multiply with our complex numbers. Okay, so you don't have to write anything down for this, but this was the discussion that we just had looking at two equations. X squared equals negative 25 and x squared equals negative 36. And the question that popped up was, okay, we're supposed to take the square root of both sides, but what's the square root of negative 36? And eventually, after some discussion and some, harassment from me about your answers, we decided there is no answer, right? Okay, so the answer to this question is there doesn't exist a real number that multiplies by itself to give you a negative answer. It's impossible. When you multiply a number by itself, it's going to be same sign times same sign. So a positive times a positive is a positive. A negative times a negative is still a positive. So to get that negative 36 by squaring something is impossible. This plagued mathematicians. They needed a solution. They couldn't have a solution because there isn't a real number that exists. So we created this set of complex numbers. I always think about the complex numbers, or the imaginary numbers as we'll call them, to be placeholders. They hold the place for a solution. It works, it's a solution. It just doesn't exist with our real number set. Okay, so it's kind of like a placeholder. And that's a weird thing to think about. I'm telling you, it's not real as in a real number, but it is a real solution that we could find. Okay, so something that's not real but exists. A little strange. Let's write this down in our notes. So we're going to call it the imaginary unit. So the mathematicians were having a heck of a time. They couldn't solve equations like x squared equals negative 25 and x squared equals negative 36. So they produced the imaginary unit. The imaginary unit is the letter I. So from now on, when you see I in class, we're going to assume it's representing the imaginary unit. And I is equal to the square root of negative 1. We don't want to write square root of negative 1. We always want to write that as I, because then it's like a slap in the face. Everybody sees the I, and we all know that's not a real number. That's an imaginary number. So we want to use that I. Does the square root of negative 1 really exist? There's no number that multiplies by itself to give us negative 1. So we're going to say that I does. So then the question is, what if I take I times I? I take I times I, I get I squared, which we have to accept this. I squared is equal to negative 1, which is a real number. You could think about this a couple of different ways. Algebraically, you could start with the imaginary unit, I equals the square root of negative 1. And you could say, in order to get I squared, I will square both sides. And when you square both sides, you'll get I squared on the left, and a square will cancel out a square root, so you get negative 1 on the right. Okay, so I squared is negative 1. You could also look at it from the reverse algebra. If I accept that I squared is equal to negative 1, then what's the value of I? Take the square root of both sides. I is equal to the square root of negative 1. Okay, but we understand that this thing is not real, this square root of negative 1. It's imaginary. I will simply be our placeholder. Okay, so are you all okay with what I'm offering you? Are you drinking my Kool-Aid? I is not a real thing, but we're going to call it a real thing. and I squared is equal to negative 1, which is real. Anybody have any questions about that? Of course. Okay, next thing. So how can you calculate an even root of a negative number? So we're going to focus on square roots. So I'm going to go back to the two that we were doing at the very beginning of class, which is the square root of negative 25. Previously we said can't do it. And I'm changing that today and saying, but you can. It's just not a real number. So we're going to break this up and we're going to say this is really the square root of negative 1 times 25. Are you okay with that? That still says negative 25. I just broke it up. And then there's a property of radicals that says as long as you're multiplying, you're allowed to break these things up and multiply the radicals. So I could say it's really the square root of negative 1 times the square root of 25. And now we can do the square roots of both of those. What is the square root of negative 1? I. And what is the square root of 25? So the answer is 5i. Now you probably won't do all this work for every problem. So if I do the square root of negative 36, the square root of negative 36 is 6i. The square root of negative 4 is, tell me, 2i. The square root of negative 100 is 10i. The square root of negative 5. Do you know the square root of 5? It's somewhere in between 2 and 3, right? Because the square root of 4 is 2 and the square root of 9 is 3. And 5 is somewhere in between 4 and 9. So we kind of know what it would be as a decimal. I don't want a decimal. I want you to leave it in radical form. All you have to do on this one is take out the negative and write it as an I. So we're going to say the square root of negative 5 is I square root 5. That's okay. But that I tells everybody in the room right away, this is not a real answer, this is an imaginary answer. So what about the square root of negative 13? I square root 13. Okay. The square root of negative 7. I square root 7. The square root of negative 18. Give me an answer. I square root 18. Perfect, and I'm going to tell you you're not done. Okay, so we have to go back. There's could be a difference between how people know how to reduce square roots. So the problem with 18 that we didn't have with 7, 13, or 5 is that 18 has a perfect square factor. There's a number that goes into it that is one of the perfect squares. Let me ask you this question. Have you ever seen your radicals reduced by using a factor tree? Okay, so we do this, most of us. We say 18 is really 9 times 2, and 9 is really 3 times 3, and we get down to what we would call the prime factors, where 3 and 2 are prime numbers, their only factors are 1 in themselves. And when you get to the bottom of the prime factors, you look at these prime factors, 3, 3, and 2. Do any of the prime factors show up twice? The 3's. For every pair that shows up, you can take one number out. So a 3 will come out of the radical. So where I had I square root 18, I can now write that as 3i. And then any number that doesn't have a match, its own partner, it has to stay inside the radical. So the square root of negative 18 is 3i square root 2. Now, the square root of positive 18 would just be 3 square root 2. But when it's negative, you'll pull an I out as well. So I could do another one like the square root of negative 8. That's I times the square root of 8. I'll do my factor tree 4 and 2, 2 and 2. And I'm looking for a pair. I got a pair of 2s. They don't have to be on the same branch set. They could be like opposite of each other or in a different area. But that will give me 2I square root 2 for the loner 2 that's left over. There will be some questions on your homework that will allow you to practice that reducing of radicals, but I want to kind of go through that. The key here is anytime you have a negative under a square root, it's your job to pull out an I. I always want to see the I instead of a negative under the square root. That way, anybody who looks at your work knows immediately they have imaginary solution. Okay. So the next thing we want to talk about is now, just in general, I had mentioned this larger set of numbers that is complex numbers. And complex numbers come in a form A plus BI, and we're going to call this standard form. So when you're working on homework, I want all of your answers to be written in standard form. So you always want to put the A or the real part first, and any part that has an I, so it's imaginary, the BI part should come second. So always try to write it in that order, A plus BI. Now we kind of had this discussion, up until this point, you only knew about real numbers. You thought real numbers was the big set of numbers, and then you could split real numbers into rational and irrational, and you could break the rationals down into integers and whole numbers and natural numbers, and you could do all those kind of subsets. I'm saying, okay, you have the real number set, but outside of that, you have this complex number set that's a lot bigger. So complex numbers are everything that's in the form A plus BI, and up until this moment, you only knew about the group that was real. So every complex number can be split up into real or imaginary. The numbers we work with on a day-to-day basis are real. They're of the form A plus BI. They all just look like A plus 0I. So if you have 0 imaginary parts, then your number is just real. So like the numbers that we count, 1, 2, 3, 4, 1 plus 0I, 2 plus 0I, 3 plus 0I, 4 plus 0I. They are complex numbers. Imaginary numbers will be numbers that come in the form A plus BI, and B is no longer equal to 0. So if I put any number other than 0, then I'm saying you have some imaginary part, and therefore you are an imaginary number. So there's this bigger set of numbers that are complex, and all the real numbers and the imaginary numbers are part of that set. Your main concern would be the standard form should look like A plus BI. I'm going to skip a few slides that we'll kind of look at later on, probably on Monday next week. But we do want to do some operations with our complex numbers. So if you want to jot these down, these are quick examples. But they would be good to have in your notebook for when you're working on your 10 questions tonight. So we want to be able to add and subtract complex numbers. Notice that when I show that I'm adding complex numbers, a lot of times, like I'll group one complex number in a set of parentheses, just to say that 3 minus 2i is a complex number, and it's made up of the real part and the imaginary part there. And then I want to add it with the other complex number that is, or the imaginary number that is 4 plus 2i. So without me telling you anything, and I just want to look at the one that's up here at the top right now, What would you tell me to do? If I said, add these two together. What would be your first instinct? Jackson? Combine like terms. Absolutely. We can treat I like any other variable. So I don't even really have to teach you anything here. You already know what you're going to do. You're going to combine the like terms. So the real parts, 3 and 4, can combine to make 7. And then the imaginary parts, a negative 2i and a positive 2i, add to make 0i. So you could write it as 7 plus 0i, but most of us would probably just write it as 7. So interestingly, you can take two imaginary answers, add them together, or two imaginary numbers, add them together, and get a real number if the imaginary parts cancel out. The same can be said for subtraction, right? Just combine like terms. The key here is you have to be careful because you want to subtract all parts of the second complex number. So you should distribute your negative. I want to subtract a negative 2, but I also want to subtract negative 3i. The most common mistake that people will make on this problem is they'll subtract negative 2i and then they'll just do minus 3i. Okay. But you actually want to do minus a negative 3i. So when I start these problems, I always change my subtraction to addition, and then I go through the next complex number and I change the sign so that I'm adding the opposite. So this is going to become plus, positive, positive. That's adding the opposite. That's what subtraction is. Adding the opposite. Once I change it all to addition, then I can go through and I can combine like terms. So again, I could combine the real parts. 8 plus 2 is 10. And I can combine the imaginary parts, the plus I and plus 3i. So I'll have 10 plus 4i. And I have my answer. Notice I write my answer in standard form. The real part 10 plus the bi is 4i. Any questions I can answer about adding or subtracting? So the other one that we want to look at is multiplication. And again, I'm going to put this out to you. Without me telling you, I think you already know what to do. So if I give you that first one, 2i times 5 plus 3i, you would tell me to do what? You can just say it. Sahil? Distribute. Yeah, distribute. So I got to do 2i times 5 and 2i plus 3i. So this can give me what? 10i plus 6i squared? Well, that's interesting. That does not look like standard form, does it? A plus bi? There should be no I squared. What do you know about I squared? I squared is -1. So when you do multiplication, and you take this 2i and you multiply it by 3i, and I times I becomes an I squared, then you're going to have to do some substitution here. So we're going to substitute -1 in for I squared, because we know from our previous notes that I squared is equal to -1. So this is going to be 10i plus 6 times -1. We'd rather see a real number of -1 than an I squared. And I'll write my final answer in standard form. So when I multiply 6 times -1, that's going to be -6. It's going to be in the front. And then plus 2i is going to come behind it. Questions about what I did right there? Yes, Kyle.
What is the knife good? I have to go behind the -6.
Like, why didn't I write it as 10i minus 6? Just because standard form is a plus bi, where the I term is always second. So, like, mathematicians are huge on standard form. So that, like, your answer looks like my answer, looks like Skylar's answer, and we all have, like, the same looking answer. It's not that 10i minus 6 would be wrong, but I just want you to write it in the standard form. Okay. Good question. So the last one here just involves a little bit more distribution, right? Some of you may say a binomial times a binomial, and you might say FOIL. You're going to take the 4 and multiply it by 3 to get 12. You're going to take 4 times the 2i to get 8i. And then you got to go back into the first binomial and pick up that negative I. Negative I times 3 is negative 3i. Negative I times positive 2i. So I think about it like the negative times a positive will be a negative. This is like 1 times 2, so 2. And I times I will be I squared. So when you have a binomial times a binomial, you should show up with 4 terms that can be simplified, right? Probably have some combining like terms, and then you've got your I squared. So positive 8i minus 3i is going to be 5i. And then I'll have minus 2 times I squared, but that's times negative 1. So then this becomes 12 plus 5i plus 2. And then I get 14 plus 5i for my final answer. Now, some of you who feel confident might not write all of those steps out. You might be able to, in your head, do negative 2 times negative 1 is plus 2i and immediately add that to 12. That's okay. So if you don't show all of those steps, that's okay. But if you're worried you might miss something, go ahead and write all the steps down. Any last questions that I can clarify for you? Okay, here is your assignment, your 10 problems for tonight.